Handout has just some formulas from three-phase circuits, since that's the most recent stuff. We should probably add before we leave here today what you need to know for transformers. You don't really need to know these formulas right here because he is probably only going to give you balanced circuits, and with balanced circuits, all you need to know is this right here, that Z delta is 3ZY. So for the delta circuit, the impedance is 3 times the, if you are transforming a Y to delta or delta to Y, that's the relationship. I didn't add on here because I figured y'all could probably figure this out, but if I take Z delta over 3, that equals ZY. So I didn't add that as a separate formula. Similarly, if you are trying to transform voltages from Y to delta, then if you have your Y voltages, you can transform them to delta by multiplying by the square root of 3 and adding 30 degrees to the angle. So how do you think you would get the, if I had the Y, what would a Y be relative to a delta? So assuming it's balanced, so YV1 would equal, say, YV12 divided by the square root of 3, and then the angle would be, you would subtract whatever it was, you'd subtract 30 degrees from each one for each phase. So that's if you needed to get the Y from a delta. I don't know that you will need to do that, but I do know that you will need to be able to figure out what the other phases, what the other phase voltages are given one phase voltage, and you'll need to know what positive sequence means and what negative sequence means, and we'll get to that when we get to that problem. So you will need to know that. So positive sequence. And let me just add to this formula right here. So this, you can say, you can write it like this. You can say it's the angle and the angle minus 120, and the original angle plus 120. But that's the same as saying it's the angle and the original angle minus 120 and the original angle minus 240 degrees, just knowing that if you get smaller than 180 or bigger than 180, you would add or subtract 360 degrees to keep your angle always between 180, negative or positive 180. So no matter how you do it, just make sure that you keep your angle in between positive 180 and negative 180. So, and just do that by adding or subtracting 360 degrees as necessary. Okay, all right. And then this is just kind of your summary of what to do if you have a three-phase network and you have to solve something from it. You take your three-phase network, and no matter what geometry or topology it has, like, you know, if it has delta, delta sources and a delta load, it doesn't really matter what topology you start with. So that's my lovely delta network there. You want to end up with Y on both of them. So you want to end up with a network that looks like this. And so you'd have like you'd have a line impedance, and he's only going to give you something that's balanced. So these are all going to have the same magnitudes, but they'll have different angles. So you'll have a line impedance, and then you'll have your load, and your loads will all be the same. And you'll have your voltages. You'll have V1, V2, V3. And so you're going to want to transform it to Y source and Y load. And you do that using those formulas on the page before. Yeah.
Is there any advantage to drawing it like that versus just doing the like regular Y?
No. It makes it look like this, so I can see that I have the same thing that I'm drawing here as here.
Gotcha.
Yeah.
The one in the middle is the Z load,
Yes.
and the what's
ZABC.
oh, so that's the impedances.
Those are the impedances. I don't know if I'm using the same letters that your book uses, but
I wouldn't know. Trust me.
yeah, it doesn't really matter. Those are the load impedances. And we'll do a problem like what I've seen. And we're going to do that very thing with this first problem. So we'll see it. So the first problem says, for the network below, generate 3 single-phase equivalent circuits and determine the complex power supplied by the 3-phase source. So we see that our source is already in a Y format. And so we don't have to transform that. If we did have to transform it, if it was delta, what we would do is we would divide each of the voltages by the square root of 3, and we would subtract each of the angles. We would subtract 30 degrees from each of the angles. So that's what you would do to transform the source side. To transform the load side, what you do is, all you have to do to go from delta to Y is to take your impedance and divide by 3. And so I get 2 minus 0.67J is my new impedance. And so then I just redraw it.
Where did you get the 3 from? I'm sorry.
It's the formula.
Oh, it's a formula.
It's a formula, yeah. It's, you can derive it, but it's just, yeah, that's how it works. Okay, so now I know that each load, what was it, 2 minus J 0.67? So that's how we transformed the load. And now we have a balanced Y-Y network, and you can divide it into 3 single-phase networks. I'm only going to draw one of them just to, because they're all the same. So I'll draw the middle one. So we would have and then that 2 ohms is the line impedance. And as you start taking power, you have to worry more about line impedances because the lines are getting long as you start moving electricity over far distances. So here we have, the single phase circuit for the middle one. And then to find I2, for instance, so I2 would just be our voltage divided by our impedance, and so I'm going to add the 2 ohms of my line to the load impedance, so I'll divide it by 4 minus J.67. Does anyone know why we use 3-phase circuits?
That's how people make the generators.
And it is, and so it's a good idea to do it that way. Do you know why they do that?
They haven't figured out a better one.
It's because, so what does AC current look like?
Something.
Yeah, yeah, but if you use a 3-phase circuit, then you end up with a nice smooth, they add together in a way to make it.
Oh yeah, because if they're at the same angle, the 2 ones that are negative will pull on the peak one. That's
Yeah, right. You have it balanced just right to make it all.
Yeah.
I didn't say that well, but it makes it smooth. So 4 minus J.667. And as a phasor, that would be let's see, 54 angle negative 110.5, I think. 54 angle negative 110.5. So amps, and from that I know what I3 is going to be because it's balanced. I know it's going to be 54, and I would subtract 120 from 110, but when I do that, I would get a number that is not between negative 180 and positive 180.
I'm getting a different answer off the calculator for I2.
Oh, okay, it's probably me.
I'm getting like 28 amps at an angle of 0.4 degrees. That could be my error.
I trust that one at an 84.
I have this. I did it here, and I got the same answers I have here. That makes me feel like I'm right.
220 angle negative 120.
Divided by 4 minus J.667.
Oh, never mind. I see where. Okay, I see where I'm wrong.
Yeah.
Clarify.
Ordinarily, I would be certain that I was wrong, except for the fact that I got the same answer as the solutions, which is
You know,
rare.
I misplaced the decimal point. That's my fault.
Okay, so then in a positive phase sequence, you subtract 120 to go from one phase to the next. So it'd be negative 110 minus 120, which would be negative 230, and then I'll add 360 to that, and I get positive 130. So I3 is going to be 54 positive 130.5. And then I1 I can either subtract 120 from I3 or add 120 to I2. So either way, I will get 54 angle 10.5? 9.5 degrees? Yeah. And these are all amps. Are they RMS?
Yeah.
Yes. Okay, now the next question says, find the complex power delivered by the source. So let's find the complex power delivered by the source. Let's just do it for the first phase. So for the first phase, at this point it should be pretty easy because we have I for phase 1 is 54 angle 9.5, and we have V1 is 220 angle 0 degrees, and so our complex power is VI star. Do I need a 1/2?
No,
Why not?
because you're not using RMS.
You are
Because I
using-
am
you are
using,
RMS.
yes, right answer, completely backwards reason, yes. Because I am using RMS, I do not need the 1/2.
What are you doing?
So that would be 220 angle 0 times 54 angle negative 9.5, which is 11.88 kilo. 11.88 angle negative 9.5 kilo somethings, kilowatts. Yes, volt amperes. That's how you measure complex power. And if we wanted to get the total complex power, it's going to be three times this value. And what is the angle going to be? So the total complex power check something real quick. I think we just say it's. Let me double check this real quick. I think the angle is the same as the first phase. Yes. So the angle will be the same as in the first phase. And so you multiply it by 3. So we'd have 3, 11.88 angle negative 9.5 kilovolt amperes, or 35.81 angle negative 9.5 kVA. Okay, so questions on that, or on the next one we're going to do is finding, given voltage as in a, just given one of the phases, finding the other phases. But if you have a question other than that, yes.
What's ST?
Total power. We just found the power for one phase, but there's three phases.
Yeah.
So I multiplied it by 3. So that's just
Oh.
total complex power.
So they're all gonna have the same complex power? Each phase?
They will have different angles.
Different angles.
That's what I was looking up to see what the total was, because I don't see why it has the same angle, but that's what my answer has, so.
So should we just use the phase that's closest to 0, or is there a guideline?
Let me find out about that. Let me pause it for a second and find out. It turns out that if you use trig identities on angle sum and angle differences, no, you don't have to. I'm just saying,
Okay,
I'm giving you
never mind.
the shortcut. I'm telling you why. So if you have the three phases, so you have positive phase sequence where you have angle theta minus 120, angle theta plus 120. If you get the powers for each of those, you would have angle theta minus 120, angle theta plus 120. And then if you add those all together, the magnitudes will add, but because of the angles, if you use the trig identities, they would all end up being that you would end up with the angle of the first phase. So that's why it was the angle of the first phase. I was right. If I had just pretended like I knew that that was what it was, without having to look up, you'd never know that I didn't know. But now we know, and we know. Okay, so there was a chat. Did I start the recording? I did start the recording. Thank you for checking. I'm going to pause for a moment and stop sharing my screen and stop sharing on that so I can look and see what I have on my computer that I feel is moral and ethical to share.